Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation FETs, a physics perspective. This is lecture number 20 and this we will be studying the SPICE models. So, just to recapitulate what we did in the previous turn or in the previous lecture, we looked into a diode, right, and the diode was looked into as a switch, because on the forward, when you do it a forward bias, the current was relatively large, and when you do the reverse bias before the breakdown, the current was relatively small. So, you can use a diode as a basic switch as well, and therefore, we also learned that in the forward bias condition the current is relatively large, right, which effectively means that the resistance offered by the diode in the forward bias is relatively small as compared to that in the reverse bias, because the reverse bias, since the current is very small, the resistance offered is very large. So, typically whenever SPICE model files are generated, they actually do the route of finding the equivalent circuit of a diode, and from there they try to extract the equations and try to emulate those equations onto the schematic. Look at this diode, this is a symbol of a diode, right, and the symbol of the diode is there, and this diode symbol is given an equivalent circuit model here, the equivalent circuit model here, right. And how do you do it? This is the source resistance of the diode itself. So, what happens is that typically any diode will have a source resistance, obviously any active device will have a resistance. So, that is emulated by this Rs, and then the Vd is the voltage across the diode and Id is the current across the diode. So, if I plot for you the IV characteristics, let us suppose like this, and then we come to this point, let us suppose x point, this is current versus voltage. Then what will happen is that as the voltage increases and somewhere around x, when the voltage is somewhere around x, the current is sort of independent of the voltage, right. The current actually increases very fast with a very small change or almost no change in the voltage, which means that the voltage across the diode is then latched to that particular value, correct, is latched to that particular value, and therefore, we say that the voltage is fixed. That voltage is given as the voltage across the diode Vd. And we will also look into the Cd, which is basically the effective capacitances which is available across the two edges of the diode. So, basically an RC element is being chosen here, and we are trying to find out an equivalent circuit of a diode. So, to do that, we already know that the forward current of a diode Id is given by this formula here, where Is is the reverse saturation current. So, this Is is my reverse saturation current, and this basically increases every 10-degree rise in temperature, doubles actually, we have already told that. And as you can see on the left hand side, on the right hand side, it is exponential QV by kT. Now, please understand that it primarily means that there is an exponential rise in the current happening. So, when V is very, very small, extremely small, close to 0, this quantity is very small, and therefore, this minus 1 will be also very small, and in the end you will get a very small current approximately equals to Is. But as you go on increasing the value of V, this exponentially rises, and therefore, this quantity shoots up, right. Whereas, on the reverse bias, when V is negative, since it is an exponentially negative quantity, this quantity happens to be negatively very small quantity, and therefore, Is is reduced to a larger extent. And therefore, this equation, also referred to as the Richardson equation, is generally favored equation for a p-n junction diode, right. Now, let us take, so this is the current equation which you see here. Also, there will be depletion layer capacitance, which I have already discussed with you in the previous class. We say Cj is the depletion junction capacitance given by Cjs, which is basically the 0 bias capacitance, divided by 1 minus V by V built in to the power m, right. So, this is basically your m, or we can refer, many books refer this as m as well as n. This is a constant which is available to you. Vbi is known as the built in potential. Now, what happens is that Cj, therefore, let me write down in a proper fashion this will, so that you can easily understand. Assuming that V m equals to 1, I can write down Cj equals to Cj0. So, basically it means that when V equals to 0, right, this all quantities equals to 1 and Cj equals to Cjs, right, this is 0 bias. Now, when you go on increasing the value of V, this quantity starts to increase, right. Therefore, 1 minus this quantity starts to decrease, which effectively means this starts to increase. So, when you go on increasing the bias in the reverse sense, your capacitance state change tends to change, right. Now, how do you define V built in, right, that is a major, if not a problem, but a major issue as far as p-n junction is diode. V built in is basically the voltage which is required or by the electron to cross the depletion region from n side to p side. So, across the hill, the minimum amount of potential required to cross the hill is basically my depletion region. So, there are 3 components here. One is the forward current, which is basically this one, and then you have a depletion layer capacitance, which is this one, and of course, the parasitic resistance, which is this one. So, this is again the parasitic resistance takes into account all the resistance of the diode in a special sense. This is a case study of using a diode device model, right. So, on the leftmost side is the schematic entry, on the middle is basically my net list, and on the right hand side you will see the result. So, this is basically a p-n junction diode, which is basically we are providing a DC bias to it, and what we will do is that we will go on increasing the DC bias in steps, and as we can see, if you go on increasing DC bias in steps, you will get some changes in the value of voltage. And if you do the analysis, you see this one was I was talking about, that I am doing a DC analysis. On whom I am doing a DC analysis? Vd, which is my this one, and I am starting with 0 volts with 800 millivolts, and the step size is 10 millivolts. So, for every 10 millivolts it will do the simulation and get the calculation, and every 10 millivolts it will recall the function of Cj, Rs and Id and try to formulate a equation to calculate the total current. Now, if you look at the way we have done it is, if you look at this particular point, I say Vd equals to N001. So, 001 is this node, let us suppose this is the node 001. So, to node 001 I have been connected Vd as also have connected the diode here, right. So, this diode has got a 1 milliampere basic current flowing, and I have a DC source which is basically initialized to 0 volts. Now, let us go to the diode model equation. When I call dot model 1 milliamp diode D and I recall Is to be equals to 100 picoampere and ideality factor of 1.6, what does it tell me is that the reverse saturation current is 100 picoamperes, and the ideality factor, which is m there, the previous graph, this m value, we referred this to be as n in some cases, will be given by 1.679. So, this is how can you fix the value? Well, the way it is done is that there is an arbitrary value given, right. Arbitrary a value has been already given to it. So, a default value is given. If you want to change it, you can do that, but the change in the value of n specifically only possible and justifiable if the doping concentration on the p and n side has changed, right, the temperature has changed and so on and so forth. So, n depends upon many other factors which is not user dependent. Now, this is the library file where we standard diode models are being extracted from. So, these are library files. So, we start with .lib. So, this is basically a .lib file. These are referred to as .lib extensions or .lib, we recall .lib files from here. And then finally, we end up having an analysis request, and this analysis request is, what is the request? It should be a DC simulation, and its initiation value is Vd, starts from 0 volts, ends at 800 millivolts, 0.8 volts with increment of 10 millivolts as you move along, right. And then on the right hand side, if you see, this is sort of a forward bias characteristics of IV characteristics of the diode. As you can see, it goes like this, and then it goes simply becomes like this in this fashion. And if you do on the log scale, it looks something like this. This is the linear scale, this is the log scale IDVD characteristics in the forward bias case, right. The model is a good way of defining the various factors responsible for diode. So, I just did it for diode for you, but the same thing is applicable for all other sort of networks or of active devices, for example, FET and so on and so forth. This we have already discussed, but I need to sort of reinforce it once again, because all of you are aware of by this time that the device model is absolutely essential in order to extract the characteristics of the device, right. Now, the problem is that experimentation can be done on any device, right, and you can extract its data. As you can see on the right hand side, the data sheet for a device RB168mm 150, and if you look at the data sheet and this is basically a diode, and you plot the forward current with respect to forward voltage, I get a somehow or other, because it is a log scale, that is the reason you are looking at it in this manner. For various values of temperature, I see currents available to you, right. As the temperature goes on increasing, the current also starts to show an increase. This is obvious because as the temperature goes on increasing, more electron hole pairs are generated, and when more electron hole pairs are generated, more current flows, and therefore, the current value for the same value of forward voltage is higher when the temperature is also higher. On the right hand side, whereas we do a simulation, you see the lines are very straight and very smooth in nature. So, you should be very careful that the simulation result is just sort of result which tries to emulate the exact nature of the diode. It is not to a larger extent the exact replica of the device itself, because as you can see here, there is a variations in the current, whereas there is no variation in the current onto the right hand side. And therefore, look at the last statement available to you. Since the simulation is based on some theoretical characterization, the results obviously cannot be satisfactory. There will be some irregular characteristics in the actual fabrication. Why? As for example, I will give you a small example to showcase this. See, till now when we were doing this diode analysis or even this equivalent circuit model, I was never telling you that the diode will be connected to an external wire by a contact. This contact will have some resistances, right, and this contact resistance will add to this value of Rs, thereby lowering the current. So, the current which you are predicting in a SPICE model, let us suppose for a very low level SPICE model, you will be basically over predicting the value of the current, whereas the actual value of the current will be relatively small in that case. So, that inherent issue is there for any model, not only SPICE, for any model, right, and you cannot help it. But what does it help me is that it gives me a first hand impression of the variation of the current with respect to voltage, capacitance with respect to voltage, even before you start doing any formal analysis of the device. So, that is the importance of a SPICE device model. Another example of SPICE, I can show it to you, a diode example, a SPICE model. So, what you see, you have a voltage source here now, and I have a diode which is connected in parallel to this voltage source with this capacitor of 1 microfarad. Let us see what will happen. So, this is my input voltage and this is my output voltage, right. Input voltage is given by this and output voltage is given by this. So, as you can see, the input and output follows each other as we move ahead, and it is very simple. This is basically also referred to as a DC restorer. I do not know how many of you have worked with it, but say for example, you want to do a clamping circuit. So, this is almost like an example of a clamped circuit. So, what we are doing is we are giving a pulse here, right, whose TR and TF are defined, and this is the millisecond range of this thing, and then we define the capacitor C1, which is this one, whose value is equals to 1 microfarad, and it is connected between the nodes in and out. So, in and out are the two nodes here, out and in, and between that you have a 1 microfarad capacitor. You have this diode D1 connected between ground 0 and out. So, it is 0 and out, and the value is and the model is 1N4148. So, when you write 1N4148, indirectly does is it tries to emulate or extract the library file of 1N4148 from the LT library file, and then they are able to do it. How do you do that? This equation I have already discussed with you. Now, the type of simulation you want to do is basically a transient analysis, right, because it is a transient response which you get, and you get transient response here. So, what should be the transient response? That, so it is 0, and then every 100 microsecond you should get a transient response. That is the order which you will get. So, when the input is sharply changing, right, that is the point when the capacitor is almost like a open circuited, and therefore, whatever input you are giving is appearing in the output, and that is the reason you see the top and bottom curves, they are emulating each other. But when the input is constant, the capacitor has actually stored the value, and that capacitor is trying to sort of put the value onto the output, and therefore, you see initially input was 7 volts has now become 9.5 volts in the input side. Why? Because diode being reversed bias is an open circuit, capacitor was storing some charge, it is now giving into the output, and therefore, the output voltage has been given a rise of approximately 1.5 volts, and you get 2.5 volts, approximately 9 volt. So this is basically a DC level shifter. So, if you look very carefully for the input voltage, I can safely say DC level is 1 volt around, and for this is approximately 3.5 volts which you will get. So, this is 3.5 and this is 1 volt. So, you see you have been able to shift the DC slightly on the higher side, right. You can also shift the DC down, I can leave an example for you to do that, right. So, this is one of the examples of diode example file I shared with you, and you can do it on any of the SPICE platform here. These two circuits I am leaving it to you as a practice circuit, right. Please try to do this as a practice for you. How will you do it? There are two ways of moving ahead. Either you do a schematic entry, or you do a netlist. Before doing that, look at the library files, library file of LTSpice. Once you look at the library file of LTSpice, check what diode are available. Is it a Zener diode, or is it an ordinary diode, or is it a varactor diode, what type of diode it is, what type of capacitors are there, what is the mean value of the capacitor, what is the tolerance of the resistor, what is the mean value of the resistor, right, and try to emulate this circuitry from the diode equation which we get. If you look carefully here, you will see that this is basically a rectifier circuit which you can work along, and I will leave for you to work on this practice circuit in a detailed manner, right. So, let us recapitulate what we learned in this short lecture here. I gave you some basic idea about device physics of diode, though not part of this syllabus, but I would recommend that you please go back to your notebooks and look at a PN junction forward and reverse bias. So, let me recapitulate what we did. We did PN junction, we did forward bias as well as on the reverse bias. In both the cases, we saw what is the breakdown voltage here, right, and what is the forward voltage here. Further, we found out that the capacitance of the diode is basically a function of the bias which you give, V bias, and in the reverse bias the depletion thickness is larger and therefore the capacitance is smaller. This we have learned one. So, and cap is therefore also a function of forward bias or reverse bias. We also learned that there is a parasitic resistance available, and this parasitic resistance is a function of many quantities which are basically dependent on the device quantities. We finally also looked into concept of V built in, right, built in voltage, and how built in voltage is referred to in this. So, built in voltage numerically is given as kT by Q, ln of NAND by Ni square. This is how you define a V built in, right. So, higher the value of NAND, more will be the value of V built in which you will require. These are all very fundamental device level understanding which you should gather while going through this course. So, we learned V built in, and then how V built in was related to the capacitance, we also learned that. So, when my applied voltage is exactly equals to V built in, we saw that this quantity V by V built in will be equals to 1, 1 minus 1 will be equals to 0, and therefore, I can safely say that my capacitance is actually infinity, right. And this happens when my applied reverse bias is approximately equals to the built in voltage of the device. Physical reason for this you need to find out. We looked into diode model files, right. These diode model files have been looked into, and also we looked into the notation for netlist. We looked to the notation for netlist and how these notations are important. And I gave you at the end of the end of the talk, we discussed about the two practice circuits, try to emulate it on the LTSpice and then try to get the value of the voltage and current in this case. I think with this I will stop at this stage and we will continue with device model in my next class. Thank you.